So I was just informed something horrible happened to this video and half of it was missing. So I don't want to leave you on a cliffhanger. So let's take a look at things again, and we're going on the conservation of momentum. Can't leave a problem unfinished because I just know that would drive everyone batty. And so now what we're looking for is the amount of wind, the force of the wind that's blowing on things in this direction. So we're not really worried about anything going on in this direction because it's just raising from the stovepipe and then it's being pushed along by the wind from left to right. From right to left. And actually I'm making the motions with my hands here and then realize that I'm not on a web camera so you guys can't see it anyway. So we're just going to worry about the X direction. And as I was starting to say, we've got our positives. So we got to remember, because we're dealing in vectors, this is important. So the sum of all of our forces in the X direction are going to be equal to the sum of our body forces and our surface forces. We have no body forces. All we have is a surface force, and what we're going to call that is the reaction in the X direction. Because it is operating in our negative direction, we're going to call that negative Rx. Because of all the assumptions that we've made previously, we're going to be able to say that this is the sum of all the mass flow rates times the x velocity. So remember that u is the x velocity out, minus the sum of all the mass flow rates times u coming into the control volume. And remember from our other slide, this is what we said the control volume was. So coming into the control volume is right here, where our stovepipe ends. Coming out of the control volume is right there. Don't care about what's going on in the inside. So as if I take a look at this, that would be Rx is equal to the mass flow rate. So we'll call this input 1, the output 2. So the mass flow rate at 2 times the, I don't know why I was putting the dot there, times the x component of the velocity at 2. Minus the mass flow rate at 1 times the x component of the velocity at 1. So as I take a look at 1, everything's coming in the y direction. It's all v. There is no u. The second part is going to fall out because there is no x component to the velocity at 1. So then we sit there and go, okay, well, negative Rx is going to be equal to mass flow rate, which we've calculated out. 179 slugs per second times our velocity. We take a look at it. Our velocity up here is 15 feet per second. But once again, vector notation. That is going in the negative direction. So that's going to be a negative 15 feet per second. That's going to be equal to negative 2.69 slug foot per second squared. Now I've got a negative on both sides, so I'll be able to say it's a positive force. It's going the way I'm going. Slug foot per second squared is not a unit of force, but we can always look at things and go, oh, that's right. Force is equal to mass times acceleration. 1 unit of force is a pound force. 1 unit of mass is the slug. 1 unit of acceleration is foot squared per second. Sorry, that is not right. It's a foot per second squared. Glad I caught myself on that one. So a slug foot per second squared, which is actually what we've got right up there, since I know that's equal to a pound force, I can say that my force of the wind that's pushing this is 2.69 pound force. And there we go.